Welcome back to Science Click. Today, we're diving into the mesmerizing world of the subatomic, where the building blocks of reality, tiny particles, dance in ways that defy our everyday intuition. Imagine a universe where everything around you, from the chair you're sitting on to the stars in the night sky, is made of these invisible specks. Each particle has unique traits, like mass or electric charge, that dictate how it moves and interacts. But what if there's another property, something so strange it reshapes our understanding of the cosmos? Buckle up, because we're about to explore a mysterious quality called spin. Picture this: it's 1922, and scientists Otto Stern and Walther Gerlach fire a beam of silver atoms through a peculiar magnetic field, one that's uneven and unpredictable. What happens next is mind-boggling. The beam doesn't just pass through, it splits clean in two. Half the particles veer upward, half downward, as if they're choosing sides in a cosmic tug-of-war. Why does this happen? Could there be two types of particles, each reacting differently to the magnetic field? Early scientists imagined electrons as tiny marbles, spinning like tops, generating miniature magnetic fields like tiny electromagnets. It's a charming image, isn't it? A microscopic world of whirling spheres. But this explanation hit a wall. For the beam to split so neatly, electrons would need to spin faster than the speed of light, an impossible feat that left physicists scratching their heads. Fast forward to today, and our most advanced model, quantum field theory, paints a different picture. Particles aren't spinning marbles, they're dimensionless points, so tiny they have no size at all. How can something with no size spin? It can't. Instead, particles possess an intrinsic property, much like mass or charge, that we call spin. This isn't a physical twirl, but a fundamental trait woven into the fabric of the universe. In this video, we'll unravel the enigma of spin, explore why that beam splits in two, and discover how this property ties not just to quantum physics but to the very geometry of space itself. Ready to have your mind twisted by rotations and group theory? Let's dive in. In mathematics, a group is like a secret club of operations that can be combined or undone. Imagine a set of quarter-turn rotations, 0 degrees, 90 degrees, 180 degrees, 270 degree, forming a group called Z4. Why Z4? Because applying one of these rotations 4 times brings you back to where you started. Think of a dazzling gemstone, its facets gleaming under light. Rotate it by 90 degrees, and it still looks the same, symmetric and unchanged. This gemstone obeys the Z4 group's rules. Now picture another stone, one that shifts appearance with each turn, revealing new colors or shapes. This one doesn't follow Z4's symmetry. Groups like these help us describe the hidden symmetries of objects, from gemstones to the very structure of space. There are countless groups out there. The hours on a clock form Z12, cycling back after 12 steps. And infinite checkerboard's movements create Z superscript 2, while all possible rotations in a circle form the S2 group, describing motion in 2 dimensions. In 3 dimensions, the SO3 group governs the rotations of space, and in the wild world of special relativity, the SO3-1 group handles the dizzying rotations of spacetime itself. But let's keep it simple and stick with our Z4 group, those 4 tidy quarter turns, to see how these ideas shape the behavior of particles. Imagine 3 gemstones. A blue one, serene and unchanging, a red one, shifting with every turn, and a green one, flipping back to its original look after just 2 rotations. Now, let's say these gemstones represent particles. As physicists, we can't see a particle's true appearance. They're fundamental, dimensionless points, the ultimate building blocks of reality. Yet, we know they can exist in different states based on their orientation. What if these states have effects we can measure in experiments? To make sense of this, let's invent an abstract state space, a kind of imaginary canvas where we map each possible state a particle can take. Rotate the red particle by 90 degrees, and its state shifts, like a dancer twirling to a new pose in this abstract space. The blue particle? It stays put, unshaken by the rotation. The green particle, though, spins twice as fast, transforming dramatically. Here's the magic. Each rotation in physical space corresponds to a rotation in this state space. We call this relationship the spin number. The blue particle has a spin number of 0. It doesn't budge. The red particle, with a spin number of 1, changes as fast as space itself. The green particle, with a spin number of 2, races through its states twice as quickly. Picture a bottle, spin 1, shifting with each turn, a button, spin 0, stubbornly static, or a playing card, spin 2, flipping back to its original face after 2 rotations. These spin numbers are like labels, classifying how particles behave under rotation. They're not just quirks, they're keys to understanding the universe's deepest symmetries. As we wrap up this page, we're left wondering, how does this abstract dance of spins connect to that split electron beam from 1922? What secrets of the cosmos are hidden in these rotations? Let's welcome back to our cosmic journey on Science Click. We're unraveling the mystery of spin, that peculiar property of particles that makes the universe tick. Last time, we imagined particles as gemstones, twirling through abstract state spaces with spin numbers 0, 1, or 2, dictating how they respond to rotations. But what does it mean for a particle's state to spin twice as fast as space itself? Simply put, the spin number tells us how quickly an object returns to its original state after a rotation. A bottle flips back after 1 full turn, a playing card after half a turn. But how do we translate this dance into the language of mathematics? Let's dive deeper into this fascinating puzzle. Physicists don't rely on everyday objects like bottles or cards to model the universe. Instead, they turn to the elegant tools of mathematics to capture the behavior of particles. Picture a spin 0 particle, like the elusive Higgs boson, as a single, unchanging point. A number that stays steady no matter how you twist or turn it. It's like a stoic lighthouse, unshaken by the storm of rotations. A spin 1 particle, like the photon that makes up light, is more dynamic, modeled as a vector, an arrow pointing in a specific direction. Rotate it, and its state shifts, much like a compass needle swinging to follow a magnetic field. Photons have a property called polarization, which only returns to its starting point after a full 360 degrees turn. This is why polarized sunglasses can block certain angles of light, creating those mesmerizing effects on a sunny day. Now, imagine a spin 2 particle, like the hypothetical graviton, the carrier of gravity. This one's modeled by a rank 2 tensor. Think of it as a double arrow, a complex structure that snaps back to its original state after just a 180 degrees rotation. In general relativity, gravity warps space in 2 perpendicular directions, like squeezing a sponge that bounces back with a half-turn symmetry. Ever seen gravitational waves rippling through the cosmos, bending space itself? Their spin 2 nature is etched into their very structure, a testament to the universe's geometric elegance. So far, we've been playing with the Z4 group, those 4 neat quarter turns. But in reality, physicists are obsessed with all possible rotations in spacetime, a far grander stage. The core idea remains: by understanding how rotations affect objects, we build a catalog of mathematical tools to describe the universe. Spin numbers aren't just labels, they're the keys to unlocking how particles like the Higgs, spin 0, photons, spin 1, or gravitons, spin 2, behave. But here's where things get wild. What about electrons and other fermions, the building blocks of matter? They don't have spin 0, 1, or 2. They have spin 1/2. Wait, how can something have half a spin? Doesn't that sound impossible? Imagine a new gemstone, shimmering with a spin of 1/2. In its abstract state space, a 360 degrees rotation in physical space only nudges its state halfway around. It takes 2 full turns, 720 degree, to bring it back to where it started. In the classical world, this sounds absurd. Spin a coffee mug 360 degrees, and it's back to normal, right? But in the quantum realm, particles like electrons defy our intuition. These spin 1/2 particles, called fermions, are the very stuff of matter. Electrons whizzing in atoms, protons and neutrons forming the nuclei of everything around us. To understand this bizarre behavior, we need to step into the strange, shimmering world of quantum mechanics. At the heart of quantum mechanics lies the superposition principle. Let's paint a picture with a simple analogy: a coin. In the classical world, a coin is either heads or tails, no in-between. But in the quantum world, before you look at it, that coin can exist in a ghostly superposition, a blend of heads and tails, hovering in a state of possibility. Only when you observe it does the universe choose heads or tails, collapsing the superposition based on probabilities. Of course, real coins don't do this. They're too big, too ordinary. But quantum particles? They live in this dreamy in-between. To model this, we create another abstract space, where heads and tails are like axes on a graph. Every superposition is a point in this space, a mix of heads and tails in any proportion. Say, 1 part heads plus 2 parts tails, or 3 heads minus 1 tails. The direction of this point determines the odds of getting heads or tails when you observe it. Lean toward the tails axis? You're more likely to see tails. Here's the kicker. In this quantum space, a state and its exact opposite, like heads and minus heads, look different mathematically but describe the same physical reality. No experiment can tell them apart. It's like two sides of the same coin, pun intended, hiding a deeper truth about the universe. This subtle idea, states that seem different but are physically identical, is the key to unlocking the mystery of spin 1/2. As we turn the page, we'll dive deeper into this quantum riddle. How does this strange property shape the behavior of electrons? And what does it reveal about the fundamental nature of reality? Let's keep exploring this cosmic dance. At the page and find out. Welcome back to Science Click, where we're unraveling the cosmic dance of particles. Last time, we stumbled upon the bizarre world of spin 1/2 particles, objects so strange they defy the rules of classical physics. How could something need 2 full turns to return to its starting point? In the everyday world, that's absurd. A single 360 degrees spin brings a coffee mug back to normal. But in the quantum realm, things get delightfully weird. Let's dive into this mind-bending story of electrons, spinners, and the secrets of the universe, painting a vivid picture as we go. Imagine a particle with a spin number of 1/2. In classical physics, a full 360 degrees rotation would flip it to the opposite of its starting state. Mathematically different, but absurdly impossible. But because opposites shouldn't exist in the physical world after a single turn. But quantum mechanics laughs at such rules. Here, a state and its opposite are physically identical, even if their mathematical descriptions differ. This quirk allows spin 1/2 particles to exist, and we model them with a mathematical marvel called a spinner. Picture a spinner as an ethereal entity, twirling in an abstract state space, needing 2 full rotations, 720 degree, to return to its original form. After 1 turn, it lands in its opposite state, yet physically, it's as if nothing has changed. Isn't that a cosmic sleight of hand? You might wonder, if a spinner looks the same after 1 turn, why care about spin 1/2? Here's where it gets intriguing. Unlike spin 0 particles, like a steady Higgs boson, or spin 1 particles, like a direction-shifting photon, spinners have unique tricks. Take 2 spinners in a field, their states rippling like waves on a pond. Combine them in a superposition, a quantum blend of states, and something magical happens. Swap one wave for its opposite, and the superposition changes, revealing subtle differences that set spinners apart. These properties make spin 1/2 particles far from ordinary. They're the rebels of the quantum world. Let's zoom in on electrons, those tiny sparks of matter with a spin number of 1/2. Electrons are modeled by a field of spinners, each spinning back to its starting state only after 2 full rotations. Imagine picking an electron at random, its state pointing like an arrow in an abstract space. We call it spin state. Physicists label the axes of this space up and down, inspired by the iconic Stern-Gerlach experiment of 1922. In that experiment, electrons shot through an uneven magnetic field split into 2 beams, one deflected up, the other down. But because their spin states align with these axes, rotate an electron 180 degrees, and a spin-up electron flips to spin down. Spin it a full 360 degrees, and it reaches its opposite state, say, minus up, But in the quantum world, this is physically the same as up. When measured, the electron randomly collapses to either up or down, like a cosmic coin toss, explaining that dramatic beam split from 1922. But why do we call it spin? Does an electron really twirl like a top? Not quite. The term comes from angular momentum, a measure of rotational motion. By studying how a particle's state shifts with a small rotation, we calculate its angular momentum. For spin 1/2 particles, this acts like an internal spinning motion, creating effects similar to a rotating object, without any actual spinning. It's as if the electron carries an invisible whirl, encoded in its quantum nature. This gets technical, so let's keep it simple. Spin is a property, like mass or charge, defined in an abstract mathematical space, not a literal pirouette.